In the last session for today, we're going to look at one more source of knowledge that you've probably already been using in the introspective judgments you've been making about preferred binomial orderings. And you may or may not already have been thinking about it. So let me illustrate it. Let's go back to the example seamstresses and bishops or bishops and seamstresses. You probably had this preference, at least at first intuitive glance, for bishops and seamstresses over seamstresses and bishops. Not everybody has that preference, but on average it's about a 70-30 preference empirically. And there may be many reasons for this preference, for this particular example. You may prefer this because you're biased toward putting words that refer to culturally more powerful or central entities before words that refer to less powerful or central entities. There's a lot of bias and injustice and in the world, and a lot of it is embedded in our preferences about how we use language. You may have preferred it, of course, for other reasons. You may have preferred it before because it was short before long. You may have preferred it because it was frequent before infrequent. Bishops is a more frequent word than seamstresses. And you may have preferred it because that order actually minimizes the number of consecutive unstressed syllables. So if we just count, bi is a stressed syllable, bi and then sha, unstressed, ps. Oh, so shups. And seam, so there's only one unstressed syllable and stresses. So you have two unstressed syllables in a row where think about seamstresses and bishops. Seam is stressed, stresses, and bishop. So we have three consecutive unstressed syllables in a row for seamstresses and bishops, and two for bishops and seamstresses. And so actually bishops and seamstresses minimizes the sort of what's called the lapse, the consecutive unstressed syllables. Now, that was probably not an incredibly strong preference, but you may have had that preference, you may not have. I'm going to look at another example. What about meat and potatoes or potatoes and meat? Which one sounds natural? Which one do you think you would probably say? And of course, surely it's obvious that you would say meat and potatoes, with the possible exception of a couple of vegetarians out there. And let's think about why you would prefer that ordering. Well, it may be because you biased before to put culturally more powerful or central referring words before ones that are words that refer to less powerful or central entities. This is an example of the condiment rule. The potatoes are stereotypically in our society the side, and the meat is the center stage of a meal. But it also might be because it was shortened before long. Meat is a shorter word in number of syllables than potatoes. Meat is also more frequent than potatoes, and potatoes and meat, maybe there's a consecutive unstressed syllable count, but it's not really that relevant for this example. But you'll notice that there's probably one more type of knowledge that's staring you in the face. It's the elephant in the room for this example that I haven't mentioned before, which is that although these cases are productive knowledge, there's also another kind of knowledge, which is that you have heard the expression meat and potatoes in your life many, many, many times, no doubt. And you've heard it a lot more than you've heard the expression potatoes and meat. So if you actually look in corpus probabilities, about 95% of these examples are going to be meat and potatoes, and only 5% potatoes and meat. So above and beyond these sources of productive knowledge, we have this another source of knowledge, which is a kind of direct experience. And so this direct experience actually is another way of managing our preferences. And of course, on average, the direct experience that will turn out will reflect the productive knowledge sources. But for any particular binomial, when we're actually deploying knowledge about language on that binomial and making an ordering judgment, we might be using direct experience, we might be using productive knowledge, or they might both be playing a role. So another part of this picture is that our logistic regression model, you can see, isn't perfectly predictive. There's a lot of error. And this is actually, so for example, there are binomials, for example, this one up here, which occurs in a particular order much more often. This is the corpus proportion. This one occurs much more often, nearly 100% of the time, in the order that we're interested in, compared to the model only predicts it about 40% of the time, and so forth. So there's a lot of noise, even though this has got also a decent predictive model. And part of that is probably that it fails to capture idiosyncrasies from direct experience. And going back to the model sort of language users as rational, let's think of what it means to be rational in the context of learning and deploying language. So if we have knowledge that can be applied both to data that we have direct experience with, tokens, lexical items, word sequences, that we have direct experience with, and to word sequences tokens, lexical items that we've never had experience with. That productive knowledge is valuable, and it may be valuable in many specific cases. But by virtue of its very nature of being productive, it's something that is ported and used across a wide variety of contexts. In contrast, we may have much more particularized experiences about cases that we have a lot of usage for. So frequent expressions, although we could use the productive knowledge, we also might as well just directly store the right conventionalized or the preferred conventionalized usage of the expression. So what should a rational learner do? Certainly a rational learner should apply productive knowledge in novel expressions where there's no direct experience to rely on. But when direct experience is plentiful, we might expect a rational learner to rely more on the direct experience, to use not only the central tendency that the productive knowledge predicts, but also the particularized knowledge that you may have of the discrepancy between the central tendency and the actual particulars for that particular multi-word expression. And we can look at that in a number of ways. So for example, here's a case where, this is a study that we did where we looked at these cases like bishops and seamstresses and bishops and just put them in sort of very vanilla contexts that aren't supposed to bias things in one way or another, and just ask which sounds better. Ask people to choose. And for example, this is a very small one study where we have only a very small number of binomials. We see that there's actually, even with a very small number of binomials, you see the powerful effect of productive of the model, this productive model's predictions. So its predictions are very nicely matching the empirical proportion that native speakers prefer. What we can also do is we can take different kinds of, we can take expressions. So a novel binomial is one that has a zero frequency effectively in the subjective experience of a native speaker. Then we can take low frequency, middle frequency, and high frequency expressions. And we might predict that if we plot, and to orient you on this graph, the x-axis is going to be this generative productive knowledge, the predictions of the model. And the y-axis is actually direct experience, the corpus probabilities. And we can hypothesize that an adult native speaker with lots of experience in their language has both. They have the productive knowledge, but they also have the direct experience. And in any particular moment, the higher the frequency, the more plentiful that direct experience, the stronger the role it's likely to play. And so what does this predict? It predicts the following. So to orient you and help you fully understand what this graph is, this is a 3D graph. So the x-axis, once again, is the model's productive knowledge predictions from our logistic regression model. The y-axis is the direct experience. And then the coloring, the shading of points, is what proportion of the time that particular ordering was chosen. So as an example, this binomial there is directness and truth. It's the model predicts that it will occur in that ordering quite infrequently, about 20% of the time, mainly because truth is a more frequent and shorter word than directness, so it should be coming before directness, not after it. But actually, this is an unusual word. So in corpus data, directness and truth is actually much more common than truth and directness. And what we see is that actually people choose something that's closer to the model proportion, a relatively low proportion. And so that's the example of an individual data point. And then the shading is basically a best fit surface of the predictions of a model that takes into account the relative contributions of both direct experience and generative knowledge. And this is also itself a logistic regression in which the direct experience and the generative knowledge are the predictors, and the weights are the relative strengths. And the relative weights are giving the shape. So because this is a horizontal gradient, generative knowledge, productive knowledge is more powerful than direct experience. And in logistic regression, I haven't told you about statistical significance, but you can also use principles of statistics to put significance levels on logistic regression outcomes. These are both direct knowledge and direct experience and generative knowledge play a role in these low frequency expressions, but the effect of generative knowledge is stronger. When we go to that's statistically significant. When we go to mid-frequency expressions, the weights are actually both considerable, but direct experience is a larger weight, and you can see that the gradient here is a little more like in that direction, so it's greater than a 45-degree angle. It's steeper in the direction of direct experience than it is in the direction of generative knowledge. And finally, for the highest frequency expressions, generative knowledge seems to play not much role at all, and it's a purely up and down gradient along direct experience. So that's the empirical landscape of how these two things are being deployed. But we can also want to try to explicitly model these idiosyncratic properties. How can we simultaneously model the simultaneous coexistence of this productive or generative knowledge and these preferences at the same time? And there's actually, it turns out there's an empirical puzzle that we can study in thinking about this. So here's the reality. If I take the binomials in this data set, the Morgan and Levy data set, and I just give a histogram of like the proportion of occurrences that occurs in alphabetical order. Why alphabetical order? It's an arbitrary decision, but it just allows us to sort of create a consistent orientation that we can use across many, many different binomials. And what you see is this interesting multimodal shape where there are lots of binomials that actually occur relatively frequently in either order, but there are also quite a few binomials at the periphery, which are what we call frozen or near frozen into only one ordering. And it more or less is obligatory which ordering you use. So for example, cat and mouse is a frozen binomial. It's only ever going to occur in that ordering, which is the alphabetical ordering. It so happens. And so cat and mouse would be right here. Okay. And then what you don't see is you don't see in the middle sections here, you don't see that many binomials that are sort of have a pretty strong preference, but it's not near frozen. Now we can ask, let's take all those binomials and we can fit them, we can push them into our logistic regression model. And we can ask, what does our logistic regression model predict? And it turns out that it does a terrible job. Okay. And in particular, what it fails to do is it fails to predict extreme ordering preferences at all. It just never gets extreme ordering preferences at all. And that's maybe, at least we can hypothesize that that's not that surprising, because the model is not set up to capture idiosyncrasies. So although cat and mouse, maybe there are some semantic constraints, although principle and interest has some semantic and some word frequency constraints going on, at the same time, these are words. These are expressions that probably live lives in our mental lexica and in our lives as a language community. And we are great learners, and we're likely to notice that specificities and remember them as direct experiences. So a complete model of the human knowledge representation of what we carry around about binomial orderings is not just about the generative knowledge, it's about the direct experience. The logistic regression model by itself doesn't give that direct experience component. So how do we capture that and capture the fact that ordering preferences for particular binomials can depart dramatically from generative knowledge? So let's go back to our logistic regression model. We had the linear predictor eta was a weighted combination of the predictors. That was passed through the sigmoid curve to get a probability of success. And we're going to revise it to add one more component. And this is going to give us what's called a beta binomial logistic regression model. So we're going to say at the beginning, we have the linear predictor, which is a weighted combination of the x's. At the end of the day, we're going to have a success probability. But what's in between the two is something a little different. We're going to use the sigmoid activation function to get a value which is a number between 0 and 1. And that's what's going to be the mean of another function, of another distribution, which is called the beta distribution. There are two different parameterizations of the beta distribution that exist. The one that we're going to be using is called the mean and concentration parameterization of the beta distribution. And so this is the mean, and this is what's called the concentration. And I will show you examples in a moment of what those are. But what we'll do is we'll say for any particular two-word combination, like pepper, comma, salt, that unordered expression, we will say it has its own value of p. And that p is going to be determined by the productive component. So this is going to be the productive knowledge that determines the linear predictor, but then the relationship between the productive knowledge's predictions and the actual preference for the binomial has this other random component, which is a draw from the beta distribution. The next question, of course, is what does the beta distribution look like? And this is your first glimpse of the beta distribution, which will come up in other contexts later on in this semester as well. The beta distribution is a probability distribution over numbers in the range 0, 1. Conceptually, you can think of it as a probability distribution over probabilities. For example, a distribution on the weighting of a coin. How likely is it to come up heads? And let's give an example of the kind of variability in beta distributions that comes from a particular mean. So this is the mean component of the beta distribution. And I'm going to show you a family of beta distributions that all have the mean of 2/3. We'll start with the highest value of the concentration parameter. So when the concentration parameter nu is 30, the orange line is the shape of the beta distribution, and you'll notice that it has a peak, which is actually, so it has a mode, and its expectation, which is the mean of the beta, is actually 2/3. So it's about here. As the concentration goes down, probability mass gets pulled away from the mode, and the distribution becomes flatter and flatter. So with nu down to 6, we have this greenish yellow line, we have the straight line of nu equals 3, and as you have a lower and lower concentration parameter, the distribution becomes what we call sparse. Values of 0 and or 1 and very close to those values become probable, and intermediate values become improbable. So for example, the lowest value that I've illustrated here, nu is equal to 0.75, is this sparse purple distribution that has one peak close to probability 0 and another peak close to probability 1. This is like a coin factory which produces extremely strongly weighted coins, most of which are virtually guaranteed to come up heads, and the remaining quarter of which are virtually guaranteed to come up tails, with an extraordinarily small number of coins that are closer to fair. The beta distribution is a great prior on success probabilities for a Bernoulli distribution. But in our case, we're not going to get into that usage just yet. We are going to use this distribution to fit and learn properties of the distribution of binomials throughout the language. And in particular, we're going to take this beta concentration parameter and we're going to vary it as a function of the overall frequency of the unordered binomial. This is the most advanced thing that we're going to be talking about today. And so the main thing is to get a qualitative sense of what we're doing. And the paper, Morgan and Levy 2015, has the details that you can go read. Parametrically, what we're going to say is, suppose that a word has frequency m sub n. Then we're going to say that the concentration parameter for its concentration parameter is going to be this function of this exponentiated linear function of the word frequency, the word log frequency. So that's overall unordered frequency, but also there's a non-parametric model, which we're not going to get into. The point is that you can fit non-parametric statistical models and get very flexible curve shapes out. So going back to the Bayes-Net view, we started out with this Bayes-Net view of logistic regression. We have all of these constraints. They collectively point to the generative or productive preference through deterministic logistic activation. And then what we've added to that original model is that mu then gets passed through this additional stochastic component, which is a draw from this beta distribution, which maybe if the concentration parameter is very high, then there's very little chance for idiosyncrasy because all the distribution probability mass is peaked close to 1 point. But if the concentration level is low, then you have a sparse distribution. If it's low enough, then the binomial is likely to be frozen in one or the other order. And so this concentration parameter governs the amount of randomness that's injected around the average value predicted by the generative or productive preference. And then finally at the end, so low concentration parameters values mean there will be lots of idiosyncrasy in the model. And then data for any particular binomial, if I get a bunch of examples of the salt, comma, pepper binomial, they come from IID, identically distributed independent draws from the same weighted coin. And that then, for fitting the model, we actually fit these parameters through Bayesian inference. And that I'm not going to get into that, but you can use Bayesian methods to fit logistic regression and more complex models like this as well. So what does it do? Let's start by looking at seeing what inferences it draws about the parameter nu. And what we see is that so log frequency, negative values are low frequency, so higher values to the right are high frequency. As we go to the right, we get lower and lower values of nu, and that corresponds to more and more idiosyncrasies. So high frequency unordered binomial expressions are likely to be more idiosyncratic, having more extreme ordering preferences being more likely to be frozen. And this has a really cool interpretation. The scientific interpretation is that an expression has to have a high enough overall frequency in order to have its own idiosyncratic life. If it's too low frequency, we'll forget about it, and its information, its knowledge won't get transmitted through speaker to speaker over generations. And so that's that. The resulting hierarchical model doesn't really do that much better than the original model in predicting any particular individual binomial. But that's actually not a problem, because the model incorporated, like if I give it a new binomial, it's going to say, well, I can make a best guess, but I also know that binomials are idiosyncratic. So the idiosyncrasy is the unpredictable part. So the biggest win is not actually from predicting particular binomial values, but by looking instead at the overall language-wide distributional properties that are predicted. If we go back to our original reality, we see this interesting multimodal distribution, which sort of has this shape. And we see that our old logistic regression model doesn't give it to us. It turns out that our new model, although it's not a perfect fit, does. When you have the hierarchical beta binomial component, and when you have the frequency sensitivity of the concentration parameter that allows more frequent binomials to behave more idiosyncratically, you actually do start to get out that interesting multimodal shape. There are lots of binomials which appear very, very easily in either order. And then there are some extreme binomials in the tails that almost exclusively occur in one order or the other. And you don't have as many in between. So that's where we're going to end with that study, but we've covered a lot of material today. In language, this is one instance. Binomials is one case study of a much more general property that we often have to model multiple overlapping defeasible constraints that drive preferences. Our example was linear ordering preferences, in particular in the binomial construction. And we introduced logistic regression, which is a very broad general purpose modeling technique. And you'll see it all over the place in machine learning, statistics. But we used it to model a particular kind of linguistic preference, almost as a little model of a piece of a grammar. It's like a fragment of the grammar, the fragment of binomial ordering preferences. This model, logistic regression, has a Bayesian interpretation, and it imposes a parametric form on the conditional distribution of outcomes given the input variables. And we saw at the end that we can extend it with a hierarchical component to handle item-specific idiosyncrasies. The version that we looked at is what's called beta binomial regression. A lot we covered today, a lot to talk about. Thank you very much, and looking forward to our discussion.